The following video is presented in partial fulfillment for the course Machine Element Design 1, taken at the University of Texas at San Antonio in the spring of 2017. This group consisted of Peter de la Cruz, Eric Duesterhoft, Gabe Motta, and Donald Perez. For a class project, we chose to analyze the rear suspension of a Formula FSAE race car built by Roadrunner Racing. The car being analyzed participated in the FSAE competition at Lincoln, Nebraska in June of 2016. This car has a triangulated 4-link Dadion beam suspension in the rear. A Dadion beam is one that is a dead axle, meaning that it does not have drive axles within the main tube section. The 4 connecting links and the beam itself are analyzed using equilibrium equations, matrix software, and SolidWorks. The objective of this report is to find the factor of safety of the beam, the links, and the hardware, as well as provide data for future teams to use in their designs. After this is done, we present options to reduce the weight of the system to increase performance. The car used Hoosier LC0 compound tires. A previous team member analyzed data from Calspan Tire Testing Consortium and found the peak coefficient of friction for these tires. The peak coefficient of friction that our member arrived at was 1.6 for the chosen tire. Specifically, this is the maximum friction available for all of the tire's dynamic behavior at any point. For example, if going around a corner, this friction capability will be split between lateral and longitudinal tractive forces developed by the tire. Using the peak coefficient friction, a known weight distribution front to rear, and the vehicle weight, it is possible to find values for the tractive forces at the tire contact patch. The lateral, longitudinal, and normal forces will all contribute to the behavior of the car. The normal force on a tire will dictate the maximum tractive force that can be developed laterally and longitudinally. In our case, assuming a weight distribution of 45, 55, and a maximum forward and lateral acceleration, we will expect to see 350 pounds of force on the rear outside tire when turning the car at the limit of the tires. This will develop a 450 pound force laterally and a 200 pound force longitudinally on the outside tire. Additionally, the inside rear tire will have a 50 pound lateral force and 25 pound force longitudinally. This was the worst case scenario, which was used to find the forces in the links and also as a load to apply to the beam in a SolidWorks assembly. All of the links will have the same diameters and wall thicknesses in this suspension. They can be analyzed for axial failure or buckling. Our analysis uses the buckling failure as our criterion because this failure will occur first and therefore must be the design parameter. The lower links are longer than the uppers, so the lower links are used as the yardstick for choosing a tube diameter and thickness. Their longer length will cause failure under a lower critical load given their identical cross-sectional profile. The analysis shows the largest force the links will experience is a 1,500 pound compressive force. Using this to be our critical load, we then found a tube diameter and thickness that would give us a factor of safety over 1 while having the smallest cross-sectional area. Because the links are long, slender, and are pinned with bolts at the beam and chassis side, they may only transmit loads axially. This is only so long as the suspension remains in the intended range of travel. If the suspension were to reach an unanticipated amount of travel, for example, the links could then see loads other than axial. It is for this reason the suspension is designed so that the beam and links will not kink and incur a catastrophic failure scenario. Using 6 equilibrium equations and treating the beam as a reference free body diagram, it is possible to determine the forces in the links with tire loads as input forces. These 6 equilibrium equations used are the sum of forces in the x, y, and z axes, as well as the sum of moments about the x, y, and z axes. Due to the longitudinal force acting on the tire and through a bearing at the beam will not incur a pitching moment from the forward motion of the car. The following are some of the connections that were used in SolidWorks. Here we have a spring, a pin, so the dampers can move up and down based upon the normal forces at the contact patches. The pink lines move to where the contact patch is, as well as the direction of the forces, although it does not tell you the magnitude. It's just a unit vector of 1. So realize that the lateral force you see there, X, is 450 pounds, and the normal, I believe, was 200. Oh, correction. Lateral force of 450 pounds at the contact patch, and also 350 pounds of normal force. That is why the Y is negative 9 inches, because it is acting at that contact patch. And what we're most worried about is the moment caused by that. And now that the study has been run, we can see these small areas of stress concentration, specifically at the welds and where the tabs meet the bearing cup. So that is failure. We use 350 megapascals as the yield strength of steel, mild steel carbon. So these are fairly thin, and they also do not have the welds added to them. The weld will add more area, so the stress concentration, of course, will reduce due to the same force acting over a larger area. And despite all these stress concentrations that predict failure, the physical beam that was constructed did not ever fail at these points, and there are no signs of failure. Again, this is the worst case loading scenario. The beam was analyzed for fatigue using zero-based loading. The worst case load scenario will be applied then removed. This is in contrast to a fully reversible load. Not accounting for the failure at the welds due to thin tabs and lack of weld, the beam is expected to endure 250,000 cycles at the worst case loading scenario. The possibility of reducing weight is one of the most important concerns on a race car. Reducing weight in the rear suspension will decrease the power needed to drive the car, increase fuel efficiency, reduce the unsprung mass, and reduce the polar moment of inertia of the car. The factor of safety of the beam is above 2, and 3 for the links. The worst point of failure was in the tabs themselves. By increasing the tab thickness and reducing sizes of material and hardware elsewhere, we can ensure that the tabs will not fail while decreasing the weight in the rest of the beam. This is a more promising style of beam we came up. It is a truss style, As we can see, there are more stress concentrations than in the original beam. However, more of the beam is green than blue. More of this material is being stressed, and the same loads that the original beam had are being distributed to more material. So as you can see, we predict a lot of failure here with the same loads and the same type of steel with a 350 megapascal failure. However, you can see that a lot of the beam is not dark blue. So we are distributing our stresses more evenly. And this is a route we think we may be taking just to utilize the material that is there. And for reference, this beam weighs 10 pounds, the original beam weighs 15 pounds. And the next study we're going to look at is the displacement of this. So this was the displacement. The scale is 8. So we do deform 7 millimeters, which is not acceptable. That's about a 1/4 inch. So that is not an acceptable amount of displacement. However, this is a first iteration of the truss style beam in order to distribute the loads more evenly throughout the material that is used. So even though this beam could not currently be put on the car for competition, it is a direction that seems more promising than just adding larger tube diameters and bigger wall thicknesses. So any metal other than steel will prove difficult to manufacture given the team's current abilities. Any sort of composites work would also have a large learning curve, and also the team does not have all of the necessary equipment to properly make structural carbon fiber parts. As with all engineering, cost is of utmost concern. If at any point the suspension becomes damaged, the more expensive it is to produce, the more expensive it will be to repair. There are over 10 versions of this beam that were created in order to make a satisfactory suspension. Through the second truss style beam, it was shown that by distributing the stresses to more members, it is possible to decrease stress concentrations. This distribution of loading to larger areas also decreases the weight of the beam at the same time. More of the material is stressed rather than in the original beam that has huge areas with very low stress. Essentially, it has large amounts of wasted material. The truss style is a more effective use of the material that needs further study before it is constructed for use on the car at competition. This report analyzed the rear suspension of an FSAE car and showed there are many areas of improvement, both to weight reduction, more efficient use of the material of the beam. We used matrices, Excel, equilibrium equations, and SolidWorks in order to show this. Our factor of safety for the beam was found to be above 2, and the factor of safety for the links and bolts is currently at 3. The expected life cycle is 250,000 at the worst case loading scenario. This will be more than sufficient for the setup, which will see roughly 100 hours of driving time. The vehicle will not spend all this operating time at the worst case scenario. We went over possible areas of improvement, including geometry changes and material changes. In keeping with the philosophy of the team, the best route would seem to be researching and designing a truss style beam to replace this current setup. Thank you.